Okay, in this video we're talking about the beginning of operations with events, so doing all kinds of different ways to combine probability. So first we want to define some set vocabulary that you might not have seen in a while. The word complement, which we've seen recently, the complement A prime of event A is going to be the set of elements not in A, but still within the sample space of the experiment. The intersection of two events, in this example, events B and C, because that's what's in the picture, the intersection is going to be the event that contains all outcomes common to B and C, also known as the overlap region. So in this Venn diagram, you can see the 7 and the 9 are in the intersection region, and therefore the set of B intersect C, and that's this symbol down here. It's the horseshoe-looking shape. Is the set 7, 9 in the curly brackets, because we're writing these as sets in set notation. The union of events B and C is the event containing all outcomes that belong to B or C or both. So this is B and C bringing everything that they have and all elements being considered. The only elements that are not considered in the union of B and C are the 2, 4, and 0 that lie outside of the two circles, but still in the sample space. The symbol for union is this inverted horseshoe, and the set here includes 1, 3, 5, 6, 7, 8, and 9. So it does indeed include the overlap region as well as the two separate circle areas inside of B and C. To use a Venn diagram to solve a probability question, you may have to do a little bit of algebra first. So here's an example. In a group of 30 students, so now we know there are 30 students represented in our Venn diagram. 17 play computer games, 10 play board games, and 9 play neither. But it doesn't tell me how many play both. So if I was going to set up this Venn diagram, I actually can't label the 17 and the 10 on it yet, assuming that there's something in the intersection, which unless it says otherwise, we have to assume that there is. And we may find out later that there's not, but we're going to assume that there is at the beginning. We know only that 9 students play neither, and let's label this one computer games and this one board games. Then 9 can be outside of those two circles, but still inside of the sample space or the universal set. I'm going to call the middle region, the intersection region, X, because I don't know how many people are in it. Now, the 17 people that play computer games do not go here in the C circle, right? It doesn't say that 17 people play computer games, but not both. It just says 17 play computer games. That means in the entire circle of C, there are 17 people. So in this region out here, it is 17 minus the intersection region of X, and I don't know what that X is yet. In the board game circle, there are 10 people all together. So in this region, outside of the intersection, I have to write 10 minus X. And now I have enough information, because every distinct region is labeled, to set up an equation. That's 17 plus X, this region, plus the middle region, plus the 10 minus X region. And those are the 3 distinct regions inside of the circles, plus the 9 that float outside, equals the 30 students in the entire class, or in the Venn diagram. And then I can solve this algebraically. This x and this x will cancel each other out. 17 plus 10 is 27. 27 minus x plus 9 equals 30. I can move the 9 to the other, oh no, actually let's move the x to the other side, make it positive, and add together the 27 and the 9 that remain, so 36 equals 30 plus x, and now I can subtract the 30 from both sides and find out that x equals 6. Now I can see that there are 6 people in the intersection region, so I can label on my Venn diagram that this is 6, which means the B circle includes 10 minus 6, so 4 people here that are not in the intersection, and 17 minus 6 would be 11 people here that are not in the intersection. I can double check that the 11, 6, 4, and 9 do indeed all add up to 30. And then I can answer probability questions. So it says, use your diagram to find the probability that a student chosen at random from the group plays board games. Well, all the board games, kids, we knew that from the beginning. That was 10 students. Okay, so let's answer part A up here, okay? 10 students out of the 30 students play board games. It doesn't say only board games, right? So I can include the 10, all the 10, 6 in the middle and the 4 that play only board. And so that's going to be 1/3 if I reduce it. Question B says a student plays both computer games and board games. We know now pretty quickly that that's the 6 in our overlap region or our intersection, and I can reduce that to 1/5. and the probability that a student plays board games but not computer games. So board games but not computer games are these 4 people. So 4 out of 30, which simplifies to 2/15 if I'm leaving my probability as a reduced fraction. Okay, so there's using a Venn diagram in a problem-solving scenario. The addition rule, so we're going on to another probability rule. This is the addition rule in general, not just for mutually exclusive events, but for any 2 events, A and B. It says that the probability of the union of A and B, which can also be read as A or B, and it's very similar to the addition rule that we wrote down in a previous lesson, says that you can add together the probabilities of A and B. But if there is an overlapping region, we have to remember to subtract it from the sum of A and B. The reason being, if I think about the probability of A, that is this entire circle. And if I think about the probability of B, that is this entire circle. So if I've added together A and B, I have added together that middle region twice. So this sort of almond-shaped region here, I've double counted it by adding together A and B, and so I need to subtract it 1 time so that it's only counted once in the union of A and B. So that's what this formula says for anything, any 2 events A and B. To get their union, you can add them together, but then you must subtract the intersection region once so that you've not double counted anything. For mutually exclusive events, the formula was just this, and we didn't need to worry about subtracting the intersection because there was no intersection. So if I scroll down, you can see another Venn diagram where the A and B events don't have an intersection, so I can just add them together to get the probability of the union of A and B, because included in the union here is this and this. So I could just add together their 2 probabilities without needing to worry about subtracting any overlap region or any intersection region. Okay. Just to remind you, you will need to know a little bit of basics about what's in a deck of cards because deck of cards questions are so common in probability. So go ahead and Google this in case if you don't know like how many diamonds there are or how many aces there are in a deck of cards, if that comes up. Now we can answer a question like this. If a card is drawn at random from an ordinary pack of 52 playing cards, let's find the probability that the card is a heart or a king. So if we consider this to be event A and this to be event B, we can use the formula that we just wrote down. I'm going to switch to a darker color here. We can use the formula that we just wrote down. The probability of being in the union of A and B, right, in either the heart or king category. Well, I can add together the probability of getting a heart plus the probability of getting a king. But then I have to remember that I have now double counted any card that is both heart and king, which we know consists of 1 card. And so I can fill in the appropriate probabilities here. So the probability of getting a heart or a king is the probability of getting a heart, and there are 13 hearts in a deck of cards, so 13 out of 52. The probability of getting a king, and there are 4 kings in a deck of cards, minus the probability of getting something that is both a heart and a king, which there is 1 in a deck of cards. So when I perform this calculation, all the denominators are already 52, so I can just add 13 plus 4 is 17, minus 1 is 16, and 16 out of 52, if you wanted to reduce it, would be what, 8 out of 26? Oh, that reduces further to 4 out of 13. Okay, that's the addition rule in action. The hardest questions we might get are these probability questions that are devoid of any kind of story. So I can still draw a Venn diagram. It's just that I don't know what the story is. I don't know if there's 5 students here or 12 students there. I just know the pure probabilities that are already given to me in the question. So this is kind of a tricky one. I have A and B are 2 events. They're telling me the probability of A. They're telling me the probability of B. And then they're telling me an equation that is true about the union. So I'm going to rewrite it a little bit clearer. It says that the probability of the union of A and B in this story, this is not to say it's always true, but in this problem, the probability of union is equal to double the probability of the intersection. So if I was going to try to imagine this on a Venn diagram and label what I'm given, I have 2 circles and I don't know their overlap region, so I would have to call it X. I know that the probability of being in the A circle, and I'm putting probabilities right onto the Venn diagram, which means that the overall probability on the Venn diagram should total up to 1. In the A circle, I have 9/20ths, but minus the x that's in the middle. That would be the probability of the middle. And in the B circle, I have 3/10ths, but minus the x that's in the middle. And then I have this other piece of information, which is that the probability of being in the union is equal to 2 times the probability of the intersection. So the probability of the union, based on the picture that I've drawn, the left side of this equation here, the probability of the union, is the 9/20ths minus x plus 3/10ths minus x. And it equals, in this problem, 2 times the probability of the intersection, which I don't know, but I have called x. And so now I have an equation that I can solve, a nice algebraic equation that I can solve to figure out what x should be. So again, these will cancel out. 9/20ths plus 3/10ths is like 9/20ths plus 6/20ths, so 15/20ths minus x equals 2x. Move that x to the other side, and 15/20ths equals 3x. I can solve this equation by passing the 20 to the other side. It'll be 15 equals 60x. And then divide both sides by 60 and find out that 1/4 equals x. So knowing that 1/4 equals x lets me come over here and label my Venn diagram more accurately. I know that there's 1/4 in here. This is going to be 3/10ths minus 1/4, which I can simplify by getting a common denominator. I'm not sure if I'm going to need it for the problem, so I might as well do it so I have everything labeled accurately. Let's get a common denominator of 40. So this one's going to be 12/40 minus 10/40, which gives me 2/40, or 1/20th. So a little bit of fraction math, or you can use a calculator if that's a calculator-enabled section. 9/20ths minus 1/4 is going to be 9/20ths minus 5/20ths, which is 4/20ths, also known as 1/5 out here. And then I know that the whole probability of the entire Venn diagram, including the rectangle, is supposed to add up to 1. So in order to figure out what remains, I'm going to want to do 1 minus the 3 regions that I have labeled already, the 3 distinct regions that I have labeled. So if I make these all have a common denominator of 20, it's 20 minus 4 minus 5 minus 1, which is 10/20ths, also known as 1/2, that remains. And now I have every region filled in. So as I've said, these are the toughest ones because it's talking pure probability with no story behind it. But once you've got your Venn diagram labeled, answering the questions is much simpler. So here we're looking at the probability of the union of A and B. Well, now I know from looking at my Venn diagram that that's going to be 1/5 plus 1/4 plus 1/20th, which is equal to 1/2. So the probability of the union of A and B is 1/2. Or I could use the formula to get that if I wanted to. I would get the same result. The probability of the union of A and B with that prime symbol next to it means the complement, or not the union of A and B. That also equals 1/2 because that's the 1/2 that sits outside of the circle. And then the probability of A intersection with not B, so the A circle, and where it intersects with the not B region. So the A circle is everything in A, but where it intersects with the not B region is what I have shaded in green now, and that's going to be 1/5. So these are the toughest ones that require the most practice, but rest assured we will practice. And then the last example is actually pretty quick. A box contains board pens of various colors. A teacher picks out a pen at random. The probability of drawing out a red pen is 1/5, and the probability of drawing out a green pen is 3/7. What is the probability of drawing neither a red nor a green pen? Because a pen cannot be red and green at the same time, if I'm trying to visualize this as a Venn diagram, I can have mutually exclusive events, red and green, and then everything outside of these circles is other, right? So the probability of drawing out a red pen is 1/5, and the probability of drawing out a green pen is 3/7. So what is the probability of drawing neither a red nor a green pen? That's talking about the region out here. So this is pretty simple. I just need to establish what 1 minus 1/5 minus 3/7 is. To get a common denominator here, I'll use 35, which means this is 21. Nope, yes, 7 out of 35. And let's see what we're doing here. Times 5. So 15 out of 35. So 35 minus 7 and minus 15 puts us at 13 out of 35 chance of getting neither red nor green. So the only added trick here was to think in advance about the events that you have to decide if they're mutually exclusive or if they have an overlap region. And that is all for now.